we did one, in the first half, we did one, that structure, sine, cosine. Yeah. A times cosine plus B times sine. That's the structure. Yeah. Undetermined coefficients, little a, little b. Yeah, those are undetermined coefficients. Yeah. So in this E.2 topic, so we need to learn, more information about that appropriate structures. Yeah. All right. Yeah. So let's look at the question. Exponential function again. Yeah. So let's look at one example first. Yeah. In this example, initial value problem, we do not use Laplace transform. Yeah. So we just use the non-Laplace transform way. Yeah. R function, this is the R function. Okay, right hand side, R function. When you see that R function, then what? Because remember, we need to determine that YP, right? Particular, the structure of this YP, this particular solution. Yeah. So what structure you want to use? That's the question. Yeah. So in this subsection, we want to, learn the rules, general rules. So to select appropriate structure for that YP function. Yeah. All right, solution. Find a particular solution, YP. Yeah. So here, YP, the undetermined part, first, this E function, so we need to, use that E function part. But before that E function, this time we select A, B, C, a quadratic, undetermined quadratic polynomial. Okay. Yeah. So you may ask, so why we select this one, quadratic undetermined? Because second degree, right? Double prime. Second degree. Okay. Second degree. So then quadratic. Third degree cubic. Yeah. Things like that. Okay, all right. So let us calculate y prime expression. Yeah. Then y double prime expression. Yeah. Then you plug in. Yeah. All right. Yeah. Okay. Yeah. Then after you get this equation, you compare the coefficients. Both sides. You compare x squared coefficients, that should be 0. Then you compare the coefficient of x term, 2c equals 6, c equals 3. There, the constant coefficient both sides. Then you get a b. Yeah. Yeah. Here, my question is, how do you know this is the correct way? Yeah. Yeah. So we can do it in this way. This is correct. But do you want the explanation? Yeah. So what is the theory behind this way? That's what we want to understand. Yeah. It's just like in the previous example, I asked you the question. So here, let's say in this way. Now you have an identity. Okay, identity. So let's say in this way. A1 cosine x plus B1 sine x equals A2 cosine x plus B2 sine x. If we know these two, this equality always, for it's correct for all x. Then the conclusion is A1 must be A2 and the B1 must be B2. Yeah. That's what we used in the previous example. Okay? All right. So here we have a situation. Yeah. We have a similar situation. Okay. The situation here is A1 plus B1x plus C1x squared equals A2 plus B2x plus C2x squared for, this is correct for all x. Then we have A1 must be equal to A2, B1 must be equal to B2, and C1 must be equal to C2. Yeah. Yeah. So can you explain why we can do things like this? Yeah. Yeah, yes. Right. Yeah. So yeah, so we can, move one side to the other side, so then we, you get A1 minus A2 time plus B1 minus B2 times x plus C1 minus C2 x squared equals 0 all the time. That means identical to 0. Okay? So this, the left-hand side quadratic polynomial, identical to 0. If a quadratic polynomial is identical to 0, then all the coefficients must be identical to 0. So, how do you explain it? So any special theorem can be used to explain this conclusion? Yeah. There is one. There is one. Yeah. There is a big theorem. That big theorem called the fundamental theorem of algebra. Okay? That theorem called the fundamental theorem of algebra. Of algebra. Okay? So you know how important it is. Yeah. That is tell us, given a polynomial of degree n, yeah, very general. So here it's quadratic, degree 2. So that one talking about a polynomial of degree m, a_n times. If that polynomial equals, that's an equation, right? Degree m. Yeah. So this degree m equation has at the most n roots. Yeah. So this equation has at most n roots. The roots could be complex roots, but n roots. Yeah. Yeah. So fundamental theorem of algebra. For any degree n polynomial, if that polynomial equals 0, you can find at the most n roots. All right? Now that's the theorem. Now we apply here. Our degree quadratic is 2. That means this polynomial has at the most 2 roots. You cannot have 3 roots. More than 2. Yeah. If it's a valid quadratic polynomial, then it has at the most 2 roots. Valid, that means the leading coefficient cannot be 0, right? Yeah. Because that degree, what's the definition of degree? The degree, the highest term, its coefficient cannot be 0. That's the meaning of that degree. Okay? Yeah. So here your degree is 2. If its leading coefficient is not 0, then it can have at the most 2 roots. But we say identical to 0, that means it equals 0 for all x, right? More than 2 roots, right? If more than two roots, the leading coefficient must be 0. Then if the leading coefficient, then we reduce the degree, right? The next degree more than 1 roots, that next the leading coefficient must be 0. So we keep doing that. All the coefficients must be 0. Okay. Even for degree n, you can have this conclusion. Degree n, at the most n roots, but we have more than n roots, right? Identical to 0. So for all x are the roots. Okay, all possible values of x, all are roots. So more than n. There. So you get all the coefficients must be 0. Yeah, that's the fundamental theorem of algebra. But for sine cosine, you cannot apply fundamental theorem of algebra, right? Sine cosine. So that's another explanation. Because sine cosine, they are linearly independent. Remember? To check linear independent, you can use the Wronskian. Yeah. Wronskian, linear independent. If linear independent, A1 must be equal to A2. B1 must be equal to B2. Otherwise, it's linearly dependent, right? Yeah. So we can also explain. Yeah. All right. Yeah. So let's continue. So here we can do it in that way. Yeah. So we can find the YP particular solution, and to find a general solution. Yeah, that's easy. Characteristic, right? Yeah. And we have C1, C2. So that term. Yeah. Yeah. So that's the first example. Yeah. All right. Yeah. Initial condition, you can determine C1, C2. Yeah. So the final solution. Yeah. All right. E.3. Then choice rules for method of undetermined coefficients. Yeah. So this part we need to understand well. Yeah. Because when you need to select the structure of YP, then it's not that simple. Yeah. Yeah. Here we have some theorem. So we have some rules we can use here. All right. Let me show you the rules. Yeah. Here it's the rules. Yeah. So I need to explain carefully the rules here. Yeah. 3 rules. Choice rules, undetermined. Yeah. So here you can see the equation. Double prime plus A y prime plus B equals R of x. Here we need to look at the structure of R function, Rx. All right. 3 rules, A, B, C, 3 rules. A rules, very simple, very straightforward. Yeah. A rule, that means if your R term takes the table 2.1, the right column, when you select YP, you just use the, right column. So, yeah. R select from the left column. Yeah, left column. Then you select the corresponding row of the right column. Yeah. Yeah. So that's simple, straightforward. Okay. So A rule is simple. All right. Basic rule, simple. B, then C rule, sum rule, also pretty simple. Yeah. Sum rule tells you if your R function is a sum of the functions at the left column. Yeah. One plus another. Then the choice of YP, the sum of the corresponding forms, adding, sum rule. That's easy, right? Okay, yeah. So the relatively hard one is the B, modification rule. We need to modify, all right? Then, so let us put our understanding, focus on B rule, modification rule. If a term in your choice for YP happens to be a solution of the homogeneous ODE, so related to the homogeneous ODE. So you find the solution of the homogeneous ODE first. Then one of the solution homogeneous appear in that R term. Yeah, if you detect, yeah. After you detect that property, then you can apply this rule. Yeah. When you apply this rule, yeah, so here you find so that structure, then you need to multiply this term, yeah, because that solution, repeated solution, yeah, that one you need to multiply that term with x. What with x if it's a single solution? Yeah, because you have two single solutions, right? But if it's a double solution, right? But because there is a possible double root, you need to multiply x squared to modify as its structure.
It's basically first order, second order, right?
First order, second order.
Is that different? For like the root or the...
Root, oh yeah.
Oh, are you talking about
right.
The double root? Is that the repeated root?
Right, repeated root,
okay.
Square, okay? Yeah, double root. So lambda minus lambda 0 square. This is double root, okay? Single root, minus lambda 1 minus lambda 2, single root and a double root, okay? Single root, you multiply x, yeah, that's enough. Double root, you need to multiply x squared, okay? All right, that's the modification rule, yeah. All right, yeah. So next, we need to understand this rule. I will use two examples to show you. One double root, one single root. Yeah. So let you feel about it. Yeah. All right, so next we will apply these rules. Yeah. Actually, these three rules we mix. Yeah. These three rules. All right, the first example, I want to show you how to work on the double root case. Yeah. And this example we did last time. Yeah. We did last time. Last time I explained in a different way. And here, after we learned these three rules, we can improve that explanation. Okay? Yeah. So I want to update it. So the example solution I show you the same as the last one, but I want to modify the explanation. Yeah. Last time the explanation is, yeah. I will talk about that later. First, let me show you the question. This same question. So you can see from our part D. Yeah, part D. Yeah. All right. So we solve it. Yeah. When we solve it, here, I just remind you, what is the structure of YP? We use CX squared, this structure. The question is, why we use this structure? Remember? Why we use this structure? Okay. My explanation the last time, I said the general case we should consider, yeah, because Y double prime, the general case, we should use a plus bx plus cx squared times e to the negative 1.5x. Okay. So in that general case, we determine a, b, c. Yeah. Then I said, because here you do not use a term, you do not use b term, you only use c term, there, if you are lucky, you can find solution. If you are not lucky, you cannot find a solution. So last time I explained in that way. So I said this way, you must be very lucky. Yeah. But actually, today after we learned those three rules, it's not just lucky because we follow that rule. We follow that modification rule. Then it's not a lucky issue. Okay? So it is guaranteed. By that modification rule, we can choose this way and it must work. The modification rule guarantees that. Yeah. So why modification rule now? Yeah, let's see. Yeah. So although here we plug in, but you will see what is the you look at the characteristic. Lambda squared plus 3 lambda plus 2.25 equals 0, then it's a double root, right? Is it plus 1.5 square equals 0? It's a double root, right? It's a double root, then this 1.5 is it corresponds to that e to the negative 1.5x. It appears in our function, right? By our modification rule, should we use the x squared multiply this function? Our multiplication rule? Yeah? Yeah, let me just go back, okay? Yeah, because here we have double root, right? Yeah, but based on this modification rule, multiply the term by this x squared, it's double root. Single root by x, double root by x squared, okay? Yeah, so now it's not lucky, right? Because we apply this rule, right? Yeah, so here I just want to, that's the modification part. Yeah, I want to explain it's not by any luck, okay? So this must work, okay? This way, yeah, it is guaranteed. Yeah.
Characteristic first.
Yes, yeah, you need to do the characteristic first. Yeah, that's correct. Yeah. All right, so then we keep going, we find c equals -5, so then we find yp, okay? Yeah, but, yeah, so before you do that, yeah, you need to, calculate lambda first. Yeah, single root, double root, yeah. Then, which yp structure you should choose. Yeah. So now you can understand better. Yeah. Here, although, so we calculate after, yeah, but this, for general solution, we calculate that. Yeah. But it's better you calculate at the beginning, okay? Yeah, calculate at the beginning. Yeah. Because you need to find general solution anyway, right? Yeah. So calculate at the beginning. Yeah. So then, because it will help you to determine the structure of yp. Yeah. So that's the, one example. Yeah. So we, improve understanding on our old example. So this is an old example. Yeah. But this time we get better understanding. Yeah. Next one, single root. Next one, because our textbook, it does not give a example about single root. So I pick one. I pick one from the exercise questions in the textbook. So then I put it here. So it's still the applied modification rule, but this time we want to look at a single root example. Yeah. So this is from the textbook. Okay. Yeah. Section 2.7 exercise. One of the exercise question, section 2.7. Okay. Yeah. So you can, 2.7. All right. Y double prime minus 16y equals the R function has two terms. Yeah. The first one, 9.6 e to the 4x, and the second term, 30 plus ex. All right, let us solve. So it's not an initial value problem. We just find a general solution of the second order ODE. Yeah. All right. Solution, this time, let's calculate the characteristic equation first. Solve the characteristic equation first. Yeah. Homogeneous. Yeah. Yeah. Two roots, two single roots, right? Yeah. So plus 4, minus 4. Yeah. Then, based on these plus 4, minus 4, you can see e to the 4x match this one, right? The first root, but not second, the first one. Yeah. Now, when we use the modification rule, it's a single root. So what structure you want to choose?
X.
Yes, x times. But you have second term, right? Second term, then you need to use the sum rule. Sum rule, okay? Plus plus some constant times e to the x. That's the sum rule. Yeah. Because this e to the x, so yeah, so here e to the x, coefficient of x is 1, right? 1 is not a root. It's not a single root. That means you don't need to multiply x, right? So you just use a constant, b times e to the x. You add this. Yeah. So it's not a root, so you do not multiply x. Okay. Yeah. Yeah. So now you get it. So homogeneous, yeah, we can write it easily. But for yp, a x times e to the 4x plus b times e to the x. Yeah. Y, yeah, here, now I hope you understand, okay? Because this is from the sum rule, okay? That b, we do not multiply x, yeah, because it's not a root, okay? That 1 is not a root. 1 times x, not a root. So we do not multiply any x. But here, this 4 is a single root, right? So we need to multiply that x. So a undetermined coefficient, capital A, and that's the right structure. Okay? Yeah.
And then all those terms are included in the final solution, the general solution, right? All 4 of those?
Yes, yes, yeah. But we need to determine capital A, capital B first. They're all included. Okay. All right. Let's calculate. Okay. Prime, double prime, plug in. Yeah. For the plug in the 16. So here, I multiply 16 to that yp. Then subtraction. When you do subtraction, it's gone. Okay. 16 is gone. Okay. And the simplification, you get you get these two terms. One a term, one b term. And r function, this is the r function. Yeah. So they are equal, so you compare the corresponding terms. Okay? Yeah. The corresponding terms, 8a equals 9.6, so a equals 1.2. Yeah. Negative 15b equals 30, so b equals negative 2. Yeah. So you write the yp solution, then your general solution. Put them together, the general solution. Yeah. Yeah. From these two examples, now you get an idea. So how to choose the appropriate structure for that yp function. Yeah. Okay. All right. Yeah. It's not very hard. Yeah. So after you understand, it is not very hard. Yeah. Okay. All right. If you do that, because if you choose more terms, the structure is not right. So then when you work on it, the coefficient of that term must be 0. Yeah, yeah. So that's something like a redundant. Yeah. Yes, yes. Yeah, you can do that, but redundant. Yeah, yeah. So here, based on these rules, you only choose the necessary terms. Yeah. So you do not choose unnecessary terms. Yeah. Okay. Yeah. So that's the main point. Yeah. Yeah. All right. Yeah. Good. Now let us move to the one example. Yeah. Our problem number 10. Word problem. Gun barrel. Yeah. So try to model. So that gun. So you shoot a bullet. Yeah. Try to model that. Okay. Yeah. Yeah. Question like this. Yeah. Solve this second order ODE, but this time the R function driving force is like that. Right. The driving force here, this graph is the driving force function. Yeah. So in the interval between 0 and pi, it is a this parabola, right? So this is a parabola curve. After that, it's 0. It's driving force 0. Yeah. Then initial condition. This models an undamped system on which a force F acts during some interval. Force on the gun barrel when a shell is fired, the barrel being break it. So this model the the breaking heavy spring. And then damp it by a dashboard. With all right. Right. So based on the model, here we only need to solve this problem. But here the problem, what's new here, right? What's new? Here is the driving force function is relatively new. The driving force function, it is a piecewise polynomial function. Two pieces, right? The first piece, it's a parabola, a quadratic polynomial. The second piece, 0. It's a constant, 0. So that's the driving force function. So when you work on it, then this time you need to, find a way. So how to handle that piecewise function. Find a particular solution, YP, here. Particular solution. So when you find that YP, you need to consider that two pieces. The first piece, so your YP should also be a quadratic polynomial. And the second piece, a constant, okay? Things like that, All right, so YP, prime, double prime, so then you plug in, original equation. So you get a, equation like that. Then you determine ABC. So you compare three coefficients. Quadratic, linear term, constant term, 3, so you can find the ABC values. Then you get a YP expression. All right. But that is for the first piece. First piece of the driving force. All right. Then the second piece. So here, the general solution. General solution for that first piece. Okay. In the interval between 0 and pi. But you need to determine capital A, capital B. In using the initial values, determine capital A, capital B. All right. Let's continue. You plug in the first initial value, you find a capital A, and then you plug in, take derivative, there, plug in, so that you get a second, the B equals 0. Then you can get a final solution. Final solution, the explicit form is like that. But this solution, that is the part between t between 0 and pi. That interval. Okay? You take the solution. After pi, then your solution is different, right? First piece. The second piece, you need to, this time, you need to solve, your driving force becomes 0. Okay? So you solve y double prime plus y, this time homogeneous, right? So you determine two new coefficients, capital C, capital D. You plug in, you can find C and D. So the second piece, you get a different function for the second piece. So then you put them together. So your solution, also you have a piecewise function as your solution. Okay? Right. So here you can think about, okay? So if we use Laplace transform, so how do you do it? Because this time you have a piecewise function. You have a piecewise function, right? Then, to use Laplace transform to solve this question, yeah, so then we need to use the new tool, because our current method, we cannot handle the piecewise function. Okay? Our basic function, in our basic formulas, there is no piecewise function. Okay? Sine, cosine, polynomial, yeah, no piecewise function. So that piecewise function, we need to, yeah, so there are some tools for the piecewise functions. We leave to module 3, that part. Module 3. So we will learn some new methods so we can work on the piecewise functions. Yeah, Laplace. Yeah. All right. Yeah.
Unit step function.
Right. Unit step, heavy side function and, delta function. Yeah. Yeah. Good. All right. So let's see if we have enough time. Yeah. So we may not have enough. Let us understand the problem first. Solution, E4. Solution by variation parameters. Yeah. So let's, just understand the general situation before we work on the solution. The solution we leave to next time. Yeah. All right. Method of variation parameters. Yeah. Here you can see if we connect to our previous method, that's the undetermined coefficients. So that means we assume the coefficients are constant. So we determine those unknown constants. That's the method. But this one, from the name of the method, variation parameters. Okay? So the parameters, the coefficient part, they are functions. The variation, function. They can vary. Okay? Yeah, those coefficients can vary. So this time we need to determine the, those functions. Yeah. Used as coefficients. Yeah. All right. Standard form. This time you can see the coefficient. It's a function, right? P function, Q function. Yeah. More general. R not identical to 0. Yeah. Non-homogeneous. But we want to find particular solution, YP. Yeah. All right. The homogeneous, yeah, first you need to look at the homogeneous. But the homogeneous, we assume we can find Y1, Y2 form a basis of solution. Yeah. So here's our, techniques we learned before. Yeah. All right. So then, Y1, Y2 are available. All right. So here you assume Y1 solution, Y2 solution for the homogeneous equation. Yeah. There. Now, next question is, how do you use Y1, Y2 to represent your YP? Yeah. Because your goal, you want to determine the structure of YP. Can you use Y1, Y2, to do some manipulation on Y1, Y2 to give you the YP representation? That's the main idea. Yeah. But here we use variation parameters. Yeah. Y1 multiply some variation function plus Y2 times some variation function adding together. Yeah, we want to, set YP structure in that way. Yeah, variation parameters. Consider the general solution. Here, YH C1Y plus C2Y, and the C1, C2, they are both constant. Yeah, not variation here. Okay, all right. Replace the parameters. This time, YP, we use U function replace C1, and the V function replace C2. Yeah. Then we need to determine U function and the V function. Yeah. All right, yeah, appropriate. So try to, if we can determine, we can find a way to calculate the u function and the v function, then we can get this yp function. So that idea, yeah, okay, yeah, just 2 minutes, yeah. Let's look at a few more. Yeah. To make it a particular solution of original ODE, yeah. Here, let me just calculate some formula, yeah, yp, yeah, based on the structure by the product rule of the derivative, so we can get yp derivative. 4 terms, relatively complicated, yeah, but just leave there, yeah, yeah. All right, make observation here. 4 terms, too complicated, right? Yeah, yeah. So here, I think, yeah, because the following discussion, it's quite long. Yeah, so let me leave next time. Yeah, yeah. So at this point, we do not have enough time. So next time, let's complete this whole method.